So here's our shortcut. We've got a few shortcuts in our arsenal. If we're at STP, we have an additional conversion. We know that 22.4 liters is equal to 1 mole. So here's how we solve it. If we have an equation, you're like, oh no, not equations. Yes, we have equations. Notice that we can solve PV equals to nRT for N. Remember that N is moles. So if we can solve this for moles, we can then use the molar relationship of 1 mole of hydrogen to 1 mole of zinc, then convert it to grams and figure out how much metal was consumed in the reaction. So let's see this in work. This is that N value solved for. So basically what it did was it just divided both sides by RT. So we take R, that's our same old R value. That's the temperature. It says STP. That's how we know it's 273.15. STP means 1 ATM. And then here we go at 2.15 liters. That was given in the problem. Notice there's no other numbers in the problem, and we can do so much math with no numbers, it feels like. So we get this number right here when we solve all of this in the calculator. And if you're not sure, everything cancels. Again, liters cancels, Kelvin cancels, and ATM cancels. All right, so now that we have that value, we can say moles of hydrogen, moles of hydrogen, moles of hydrogen, that's that number, compared to moles of zinc. And once we know moles of zinc, we can go to grams, and this part right here is from the periodic chart. Yes, we can combine any of those gas laws that have N in them with a reaction that's balanced. And that's how many grams were used to collect that much hydrogen gas. So that's one way to solve an ideal gas equation. I know it says with shortcuts. So that was a short way of solving a gas problem. I'll show you another way in a minute. It's right here. So is there a faster way? Can you use the fact that it's at STP? Yeah, you can. So we know that we have 2.15 liters of hydrogen gas. Now, we also know because it's at STP, you can only do that as STP, 1 mole is 22.4 liters. This is of the hydrogen gas, right? Oh, look, now we're in moles of hydrogen gas. Now we'll go from moles of hydrogen gas to moles of zinc, and then we'll go from moles of zinc to grams of zinc. And again, this was 1 to 1. Those were the coefficients. And then this is 1 to 75.28 grams of zinc from the periodic chart. You see how that's less math? Do you see how this is helpful and saves you time? So that's the first trick. This is called the STP trick, if you want. That's just my name for it. This is STP, though. STP and reactions. All right, now we're going to solve another problem 2 ways, the long way and the short way. So coefficient moles and volume. So when we have 1 mole of nitrogen and 3 moles, 1, 2, 3 of hydrogen, we already know that it makes 2 moles of NH3. Now, the strange thing about these gases is that even though I have more volume on the left, you can have different volumes on the left and the right because we're making something that's kind of tighter, like a tighter little molecule. It doesn't have to take up as much volume. So we have this relationship right here. In the same container, we know that the volumes are proportional. So do you see how this is 1 volume of N2 are proportional to 3 volumes of H2, and it's proportional to 2 volumes of NH3. So the volume could be anything. We're going to pick a useful unit for the ratio, and usually it's just easier with gases, like up here, to use this liters ratio. It's easier to do a liters ratio. So here's one ratio, and here's another ratio. These are meaning the same thing. So let's see this in action. All right, so here's the long way to solve this problem. Nitrogen reacts with oxygen to form dinitrogen pentoxide. Here's the reaction over here, it's balanced. What volume of oxygen is required to produce this much of him? So we're producing this, and it wants to know how much oxygen is going to be required. Notice that we have a temperature, and we have a pressure, and we have a volume. So the long way, again, is to begin with what you know, which is that dinitrogen pentoxide. Divide both sides by RT. And we can take the numbers from the problem. So we have our pressure, which is 1 atm. We have our 12.6, our 12.5, which is our liters. Our 0.0821, you know all about that one. And here is our Kelvin value. So all that's from the problem. All the problem numbers are in there. When you put it in your calculator, you're going to 1.53 moles of that. Then, like before, you're going to have to do 1.53 moles. You're going to use that molar ratio. So again, the 2 to the 5. And you're going to end up with moles of oxygen. It doesn't want to know moles of oxygen. It wants to know the volume of oxygen. So guess what? Now you get to plug that into another PV equals nRT. This PV equals nRT was for 2 to 5. This PV nRT is for oxygen. It's rearranged solving for that. And you can see here is where it goes in. That's your normal R, there's your temperature, and there's your ATMs. Now see, if it was a container and it was just holding all of it, if it gives you these values for one gas, it's also the value for the other gas because they all are in that same container. And then we get this answer right here. That's using the PV equals nRT equation twice and using a molar conversion. Is there a faster way? Oh yes. So we're going to use the volume relationship that we were just talking about up here. So our volume relationship is that we have 2 liters of N2 that are proportional to 5 liters of O2 that are proportional to 2 liters of N2O5. So we'll take our 12.5 liters, and this is 12.5 liters of the dinitrogen pentoxide. And we're going to say that in 2 liters of dinitrogen pentoxide, we have 5 liters of O2. You do the math on that, you're going to end up with 31.2 liters of O2. Wow, that was a lot less math. So now you try it on this problem. Just pause the video, and I'm going to solve it. So it wants to know what volume of hydrogen gas is produced from this many liters of iodine. Now this doesn't say STP. The STP is only when we're trying to relate moles to a certain volume. As long as you have a fully gas reaction or you're just comparing the gas components, you can always do a relationship between those liters. You can say that 1 liter of ATM is proportional to 1 liter of I2, which is proportional to 2 liters of HI. So we're going to take 2.67 liters of iodine, and in 1 liter of iodine, we have 2 liters of HI. When you put that in your calculator, you're going to get 5.34 liters. Isn't that math so much easier?